The last thing we did was to model the crack growth rate as the central quantity in our analysis as being related to the stress intensity range, which is F delta S, the range of the load, root pi A, at any stage of the crack propagation, crack growth. And we put a factor and an exponent to make that relation, in an attempt to make that relation a little bit more accurate through these material parameters C and M. So this is the Paris equation, which says that, well, the crack is growing because we have cyclic loading, and moreover the rate at which it is growing is increasing with the crack size because delta K depends on the crack size. So it captures the fundamentals of crack growth. It's the simplest relation you could possibly write. So what we can do is we can take the log of both sides. So I can write log dA dN, and if I take the log of the other side as well, what we get is a linear relation that relates the logarithm of the crack growth rate to the logarithm of the stress intensity range. So in other words, if this proposal is indeed true, when I do experiments, I should get data points for crack growth rate versus delta K in the logarithmic space, such that the points should lie on a line, because that's what the model predicts. So if we go ahead, therefore, and plot the logarithm of the stress intensity range, okay, remember it has units MPa square root meters, versus the logarithm of the crack growth rate, so let's say dA dN. Now the typical units for this is millimeters per cycle. Okay, because the growth rate is already small, we just use it in terms of millimeters so that we get some appreciable amounts. So the numbers I'm about to write is replicating, they will help replicate a figure from the book. Certainly they have to do a material and a certain test setup, etc. But it will give us an idea as to what happens physically as well. So these are not, let me say, numbers that apply, and for that matter, the shape of the line I'm about to draw, aside from its qualitative features, the exact shape will, to a certain extent, depend on the material. But what our goal here is it's to give us an idea about the general characteristics. So the size, the range of the stress intensity range goes from 5 to 100 in this case, a logarithmic scale, and the crack growth rate can be extremely small, 10 to the minus 7, okay, and all the way up to 10 to the minus 2. So 10 to the minus 7 is probably just to indicate that it is beyond our measurement. It's almost zero. So it's angstrom, right? 10 to the minus 7 millimeters. But that's what we have in the figure. So that's on the log scale, crack growth rate versus the stress intensity range. And now our relation says that in the logarithmic space, the relation between the two axes is linear. Okay, so I'm gonna draw a line. The slope of that line is m, and its position is controlled through the logarithm of c. All right. So let us go ahead and draw a line. a line. That would be the Paris prediction. We have the Paris equation, this equation, and its prediction is a line. So now what we're going to do is we're going to do an experiment. And the experiment will help us assess whether the model prediction is correct, or in fact, it's of course the other way around. First you do the experiment and then you try to model it. And in this case, the model is going to be a line. So we're going to collect data. So we're going to take a specimen. Suppose it has a certain crack size. We can take many different specimens, impose on them different delta K's and measure the rate at which the crack grows in each specimen. And for a given delta K, I can plot the rate of growth of the crack. I can measure it from subsequent values of the crack size, and I can plot the values here. Or what I can do is I can take a single specimen, as for instance here. I can start with the initial size and I can keep cycling it. For a given delta K, it will have a certain growth rate, and then as the crack grows, delta K will certainly increase, the crack growth rate will change, and I can continuously monitor the crack growth rate and plot the corresponding points over here. So either way, we're going to collect data, and that data is going to, it turns out, look like this. So of course, it is not a perfect data ever. There will be points that lie here and there, but eventually what one observes is that the data looks more or less like that. Okay, so now what is it that we are observing? So incidentally, here I should also write that the value of the stress range, which ultimately goes into delta K, the intensity range, does matter, but so does the value of the stress ratio, the ratio of S min to S max. So in this particular case, the ratio is 0.1. This is just to emphasize that eventually the value of R will also matter. So we're gonna think about how to incorporate that. So, but let's go back and have a look at the indications of the measurements. So there are a number of things that we can immediately recognize. So first of all, we can divide this plot into three distinct regimes. The intermediate regime is qualitatively, not number-wise. Don't look at the values of the crack growth rate or, for that matter, of delta K. What we're looking at is the trend in the data points, right? So this is data points, data, and this is our model, the Paris equation. So what the data points are doing is, well, there is a certain range, and this lies in the intermediate portion of the two edges, so it is indeed called the intermediate range, where the data points lie perfectly on a line, okay? And that's why we are drawing a line through those data points. So in that intermediate range, it turns out that to a very good approximation, indeed, the crack growth rate in the logarithmic space is proportional to the stress intensity range, or in our actual formulation, it means that Paris equation holds. In other words, the relation between dAdn and delta K is of power form. Okay, well, that's great. So in fact, that is the motivation for the Paris equation. You first do the experiment, you see that there is an intermediate range where the data in the log-log plot falls almost on a line, and that motivates you to write or propose the Paris equation. But now there are two other regions. So first of all, there is the high range. Now, the high range is where the crack growth rate deviates from being linear in the log-log scale, linear with respect to delta K, but it increases much faster than the rate at which delta K changes. So the Paris equation cannot capture that. So that is a deficiency of the Paris equation. In other words, if you relate dAn to dAdn to delta K through that relation where C and M are constants, then necessarily you proceed on a red line, whereas the actual data as the crack grows becomes steeper and steeper. In other words, what the data is telling us is that the crack growth rate becomes much faster as you approach a certain point where delta K is very high. This is the point, this is the region where failure is happening. So you are going here towards fracture. The crack becomes so large. So remember from the first discussions of fracture, the peeling experiment. Initially, the crack, the tape peels off slowly, but towards the very end, it starts to tear off, the peel off from the surface very rapidly at an increasing rate. So this is what is exactly happening here as well. It's growing. Now, in that case, I know the load was static, but qualitatively, if we think about the rate at which crack grows, the same thing is happening here. It is slow. It initially is increasing at a certain rate. The rate completely increases as well. You see the rate is also increasing, but the speed with which the rate changes becomes increasingly higher, and that takes us to fracture when the material eventually fails. So that's the high range. The model, the Paris equation, is unable to do well or predict meaningful results in that region. And what it will do is, obviously, is also being under-conservative. So it's not conservative. Under-conservative means that it's going to predict, well, if you want to take the crack size from 1 millimeter to 2 millimeters, you can cycle for 1,000 cycles, but in reality it will only take a few cycles because the crack growth rate actually is a lot higher. So if you work according to the model, your predictions of the number of cycles to failure beyond that point is going to be under conservative. It's not going to be a good prediction. You're going to say there is no failure, although in reality there will ultimately be failure. Now, if we look into the other extreme, there is this range, which is, let's call that the low range. Now, in the low range, something slightly different happens. In fact, it's the opposite. Well, here, the crack growth rates are very, very small. Yes, they are changing also very rapidly. They are changing very rapidly. It's not a line. But the red line in this case will lie above the green line. So in reality, here, if you want to do a very good prediction, you have to have a model that is able to fit this region of the plot very well as well. But if you use the red line, what the red line predicts always is a crack growth rate that is higher than the crack growth rate of real experimental data. So in this region, if you want to predict the number of cycles for the crack to grow from, let's say, 1 micrometer to 2 micrometers, in reality it will take, let's say, 1,000 cycles. You will predict 10 cycles. Okay? So you are now being conservative. Okay? So in that sense, extrapolating your prediction, your linear relation in the log-log scale, down into the low range, where that prediction always lies above the data, is conservative. So it turns out we are going to preserve this portion of the plot. So in other words, we're going to stick to a conservative range. So in this range, also what will happen is that, notice there is a certain change in delta K, and delta K is proportional to square root of the crack size. So when the value of delta K changes from 10 to 100, really the crack size is increasing by 2 orders of magnitude, by a factor of almost 100. Whereas here the change in delta K is small, so the change in the crack size is very, very small. So it doesn't necessarily mean that the number of cycles we spend here is small, but really the criticality of the situation will start after a certain crack size. If it's very small and it's going to take a high number of cycles for the crack to grow to another very small number, I wouldn't really care that much. But after a while, when the crack reaches a certain value, then I will really care about how much time it will take for that crack to grow to an appreciable value. So eventually, from all of that discussion, what emanates is that it is safe, more or less safe, to work with this conservative prediction, this line, even in the low range, and then extrapolate that safely into the intermediate range, where actually, well, let me put the other way. In the intermediate range, it works very well. We extrapolate it conservatively into the low range and make our predictions safely all throughout that region within some level of confidence depending on the experimental evidence that we have. Now, but on the other hand, there is certainly an issue here. In this region, the way I want my model to work is, so my model is going to move along a line up into the border of the high range, but then I would prefer the model to curve up like this. It may not fit the data very well, it depends on the quality of my model, but at least I don't want it to remain as a line. So the model, if it is improved, will be the solid red line. That's ultimately my goal. Presently what I have is my dashed line, which is the Paris equation. Still, it's not bad. It works very well up into the high range, but then in the high range, it sort of stops to function well. Now, finally, there is one additional piece of information that we have from the physics of crack growth. There actually exists a certain K value, delta K value, let's call it delta K TH, where TH stands for threshold, okay, below which the crack growth rate is 0. Okay, so if I have a certain crack size and if I don't put a lot of load on it, then I observe from experiments that sometimes, maybe not always, but sometimes the crack will just not grow. So we've said that the cracks will grow if you cycle the load. For most magnitudes of load cycling, or amplitudes of load cycling, that is indeed the case, but it turns out for some materials and for certain limits to the range of the load, or more properly, limits to the stress intensity range, there is a certain threshold value below which crack would stop propagating. So that is also a very interesting piece of information that comes from the monitoring of a single crack, because eventually we are going to see, when we look at the more, let me say, complicated in terms of the phenomenology that is involved, when we look at the more complicated case of fatigue, high cycle fatigue in particular, we're going to see that there are certain materials, in particular aluminum, to which if you impose a stress range that is smaller than a certain value, it will not fatigue. You can cycle it back and forth forever, and that is actually a key piece of design information. If you can ensure that your load range is below a certain threshold value, you don't have to worry about fatigue. Okay, but if the material does not display such a threshold, or if your stress intensity range is sufficiently high, or if the crack has grown beyond a certain value, despite the fact that delta S is small, crack is so large that delta K is beyond the threshold value, then you should start to worry about crack growth. And that is eventually our concern. So what we've concluded in this discussion is that we have a Paris equation. The Paris equation does work very well up into the high range, where we start to close up towards fracture. There it doesn't do well. We can do something to improve it, but presently its prediction in that range is under conservative. So up to that point we're doing well. After that point we need to think about how to incorporate that speed up in the rate. All right.